But frame buffer operations, as we call them. First, I just want to get a slide, an old slide, which is this drawing of the pipeline. And again, remember that there are many different ways of. I can almost not fit it here, but yeah, but then it's hard to read. Oh, it's actually okay. That's okay. There are many different ways to represent the pipeline, and if you wanted to draw the actual pipeline of an actual GPU, there would be a lot of boxes. It would be a very long thing, and maybe some branches and stuff. But this is basically the representation that is in the Wikibook, and I think it's a very good simplification because it's the main areas that we focus on. And this topic is about the last box. So here it's called per fragment operations, and you can also call it frame buffer operations. Basically, the fragment shading step outputs fragments, which is almost the same as pixels. It's a bunch of colors for pixels. And what happens in this stage is that these pixels are put in the frame buffer. And the frame buffer is like the screen. It's the array of pixels that is the screen. And there are some operations, some stuff happening here. So it's not just putting a fragment on a pixel. There are a few things that are done, a few operations that are done to achieve some extra effects like blending and depth buffering. So this is where we are right now in the pipeline. So first we're going to talk about the most used kind of blending, which is of course alpha blending. I actually wanted a little snippet from another old slide, which is this one. Yeah, remember this is the slide about what the fragment shader does. So the previous step in the pipeline, the fragment shading step. Fragment shader, again, to just repeat this mantra that shader is a small program. A shader is a little program that's executed by the GPU. And the fragment shader is a little GPU program that just calculates a color for one pixel on the screen based on some inputs. So these are the various inputs, and here is the color that is output. So I'm going to grab this little piece here and make it a little smaller. It's a little easier to read on the actual slide. It's just the screen resolution is really poor here, so this is maybe a little bit bigger. There we go. We get this fragment color out. And the fragment color is it's like a 4-dimensional vector. It's RGBA values. And the A, of course, is alpha. It's an alpha value. So it's used to control this blending stage, and it doesn't show on the screen as such. It's just used to control how the blending happens. I'm going to draw a little piece of what could be the frame buffer. So a few lines. Frame buffer, as I said, is an array of pixels. It's what we see on the screen. And the reason it's called a frame buffer is because we usually deal with animation, with something that's moving, so it's updated a number of times every second, and each time it's updated we call a frame. So that's a little piece of the frame buffer maybe. And this color is then put in a pixel. It belongs to a certain pixel. The hardware already knows. Now we are drawing this particular pixel. We execute the fragment shader for this pixel, and we get a value. And now we want to put it on the screen. And what the hardware then does is based on the fragment's alpha value. Combines the fragment color with the previous color in the frame buffer. So with alpha blending, we don't just override what's in the frame buffer, we take what is already there and we combine it, do a linear combination of what is already there and what we have calculated we should put, and the result is then put back into the frame buffer. So this is how we can do, we mainly use, I have a little drawing here with, this is typically what we use alpha blending for, is to make stuff transparent. So we can control the transparency. Now this is maybe a textbook example, because a transparent teapot is not usually what we want. We can have transparent objects in games and other applications, sure, like windows, but also a lot of the times we have transparent bits on textures. So we maybe have some opaque part of textures, and then maybe some transparent bits on the textures, like the edges, or this is a more common use. Put this here as well, just as a kind of a use case. And alpha is used to make stuff transparent. Now if you just say that at the exam, then you have a point. Well, it's not an oral exam, so. But
Probably still say it.
It might help. I wanted to put a little example with some colors. Also to show what the actual method is that's happening with alpha blending. It's, as I said, it's a simple linear combination. So let's say we have a red pixel, a red fragment. So the fragment shader calculated it wants to draw now this completely red color. And we say that in the frame buffer already is maybe a blue. And one more value, actually this is not enough, because we need to say what is the alpha value, right? We can't see that. So we say that that's 0.5. That's also calculated by the fragment shader. So it might have been looked up in a texture, or it might have been a uniform value, like in this case where the entire thing was set to be semi-transparent. This will be dark purple. Because it sort of takes half the input color and half the output color and adds the result together. Just a minute, I just need the color menu, or the color thing. So it would be like half the red. It will be reduced to half because of the half factor, and the blue will also be reduced to half. So it'll be something like this. Dark purple. And I'm going to put the equation, the actual calculation that's happening. So this is the color. So it takes the RGB of the color, and then it uses the alpha to multiply that, so it'll be like 1 minus A. And then there's a plus. It's an additive thing. And this is the blue color. This is the color that's already in the frame buffer, and that's multiplied by the alpha value itself. Oops. And then the result, 0.5, 0, 0.5. Yeah. So this is the calculation that the hardware does, and this is an example of the formula for alpha blending. If you replace the color with just a generic value, then you have the generic equation for alpha blending. Oops. Okay, another example, additive blending, which is also the other kind of blending that we use a lot. So I'll start with, no, just put the headline first. Additive blending. That's an example of what it might be used for. This one. That's big. This is an example of what you could use additive blending for. This is a bunch of particles. I guess it should look like a sun or something, or maybe an explosion. And it's probably a bunch of particles, a lot of little things that are drawn together, and they are drawn using additive blending. So the background is black, and then each object has this yellowish color. So when you draw a lot of those on top, then the value gets higher and higher because it's just additive. It just adds to what is in the frame buffer, and eventually it becomes white, which is the maximum value you can have in the frame buffer. So the value is capped. So that's why the inside of this object is completely white, although the edges are blue. It's made from yellow. Yellow. It's made from yellow objects. Yeah. So we have a similar thing going on. Just grab this from the other one. Oh, I should actually grab this whole thing. It would be easier. It would be easier. Not this one. There it is. Almost there now. What happened there? Sorry about this.
That's okay.
Really struggling with this screen here.
I don't have anything better to do anyway.
That's good. Okay. Yeah, that's actually pretty good. Just put the color value again. It's the same as before. Yeah. And as I said with this, what happens is we simply have an add. So the alpha is not actually used normally. It could maybe be used, but it's in the most simple case, it's not used at all. So it just takes the RGB, ignores the alpha, and adds it to the previous color in the frame buffer. So if we do the same operation here, we'll get a bright purple instead, because the two values will be added together. So we'll take a red fragment which is being drawn, and it's drawn in a pixel in the frame buffer which is already colored. It's blue by some previous operation, some other object we can see maybe behind this object, and the result would be purple because it's like the full red and the full blue added together, so it's 255, 0, 255. That will be the result. And this equation is simpler. It's just completely ignores the alpha value. One, 0, 1. Really bugging me today, this thing. Okay, let's get that out of the way. It's actually a little simpler. So the second half, the other operation we're going to talk about is, apart from blending, I should, just before I move on to that, say that these are just two examples of blending. What you can do with the hardware is that you control the way this equation works in the blending stage. It's not actually programmable, like you can't write code for it. That would be nice, but that's not supported on GPUs today. So what you can do is usually you can control some factors. So you usually have the equation is like fixed like this in the hardware, but you can usually control which operation is done. So you can do additive blending or multiplicative blending, or you can do subtractive. So you can just change this operation basically, and you can change the way that the pre-multiplication that happens here. So you saw in the alpha blending that the color was multiplied by here 1 minus alpha, and here it was multiplied by the alpha value. So you can usually control those and say the source color should be multiplied by 1 minus alpha, and the destination color should maybe not be multiplied by anything. And you can do that sort of freely, so you can construct various ways of blending, or various techniques of blending, and there are other effects you can achieve with that, like multiplicative blending. Also something called pre-multiplied alpha, which is a different equation also. So, now we're going to talk about depth buffering. And before I talk about depth buffering, I'm going to show you something about what is depth sorting. What do we mean when we say depth sorting? Let's put some examples. So I draw an example with some polygons that are on top of each other. So here's a why can't I do that? Oh, so. And we want a third one as well. Like this. So this is maybe not so realistic, but we could have a scene with like these three triangles in them that are separate from each other. And the point is that when we look at the graphics, we just assume that the hardware is able to do it correctly because this is what happens in real life. The point is that the red triangle is behind the other two. There's this depth order to them that means that they're drawn in a certain order. So there is something called the painter's algorithm, which is like you imagine you have a painter who wants to paint this correctly, like a perspective drawing. So the way that he makes sure that it's kind of simple really, but the way that he makes sure that everything is in the correct order, is drawn in the correct order, is that he draws it in the order of depth. So he does like what I did. He starts drawing the red triangle, and then he draws the green one, and then he draws the blue one. And if he had done it another way, it would have looked different. So it would have looked wrong because it's supposed to look like this because the blue triangle is closer to us than the green, and the green is closer than the red. And the computer must do the same thing. Geometry must be drawn in the correct order. And we call that order back to front. So we start at the back of the scene and draw everything that's most distant, and then we draw stuff a little bit closer and so on until we've drawn everything. But we do it in that order, and that makes the scene look correct. Just note what I said here. So the computer could, of course, the computer needs to do this sorting that I sort of did in my head. So I maybe looked at the scene and said, well, this object is the farthest and this object is closer. But you could have a very large scene with a lot of objects, so it's a sort basically. You sort all the objects based on the depth to the camera. So how far are they on the camera? And when you've done that, then you're able to do this. You can draw the scene back to front because you know the order of the object with respect to the depth. And it's important that it's of course the depth with respect to the camera point of view. It's not the scene world or something like that. And that also means that that we have to perform this depth sorting continuously. If we move the camera, then the order can actually change. Like if we were to look at this scene from the side or behind, then there will be a different ordering. So suddenly the order will change. So that means the computer actually has to do it every frame because stuff changes. I'm going to just put some denominations on these. So A, B, C. And then here, first C, then B, then A. And this word, painter's algorithm. This is sometimes used. We have depth buffering, which is basically a way to avoid having to do this, because sorting can be expensive when we have large scenes. But we cannot always use depth buffering because it has certain limitations. So in those cases, actually, if we want to draw stuff correctly, we have to use this painter's algorithm. I think probably this is, for instance, true with transparent stuff. So we have some transparent objects. We cannot use the depth buffer to avoid having to sort them. We actually have to use the painter's algorithm to draw them correctly. And probably, if you do that kind of thing in Unity, it has a painter's algorithm built in that switches on automatically and does this for you. I think. I'm not sure, but I think so. So, finally, what is this depth buffering? Yeah, I need something from the earlier slide. Grab this. Oh, it's already there. Just 1 minute. There. It's another thing that happens in this stage. That's why we want this drawing. Depth buffering. Copy and paste. Hey. So remember that this is the frame buffer. With depth buffering, we have another buffer, which is called the depth buffer, and it's a similar size really. It takes as much memory usually. And it has the same dimensions and resolution, so for every pixel in the frame buffer there is a corresponding pixel value in the depth buffer. And what we want to use this for is to store the depth of what we have drawn. So when we draw a fragment from a primitive, some piece of geometry in the frame buffer, some color that we should look at, we also store the depth, the distance from the camera of this particular fragment in the depth buffer. So I'm going to illustrate that. This depth value is calculated by the fragment shader, just like the color. So it's actually another output that there is from the fragment shader. If we use depth buffering, there is this other fragment. Depth value. Oh, got another word here. Fragment depth. And then when this is output, the hardware simply puts that in the depth buffer. Like this. And then the trick is that every time we draw something, we actually start by looking in the depth buffer. So if there is a fragment being drawn which is actually behind something else that has already been drawn, then we can see this in the depth buffer because the depth value of what we're drawing will be larger than the depth value that's already in the depth buffer. And in this case we just discard the fragment. The whole point of this is that we don't want the order that we draw things in to matter. So we want it to look the same regardless of whether we draw an object that is close by and then the distant object, or the other way around. That will give the same result because of this trick, this technique. And that is very nice for the hardware, because then the hardware doesn't need to spend time sorting all the geometry with the painter's algorithm, which would be very slow with very large scenes. You can't just sort the objects because they might be very close to each other, so sometimes you have to sort the actual polygons or geometry themselves, so that can be really expensive. So let me put that in words. Fragment right. We first compare new depth value to the one already in the depth buffer. And then there's like these two cases, like if the fragment's depth is less than the buffer depth, so what is already there, then we overwrite because we have an object, we're drawing an object that is closer to us than what was previously there. Put this also. Depth larger than buffer depth. And important to note is that we both override the color in the frame buffer and the depth. Because this fragment actually occludes what was there before. So what was there before can no longer be seen because it's now replaced. And in this case we do nothing. Sometimes I call this discard the fragment. A new fragment. And this is because the fragment is, we have found using the depth buffer that this new fragment is actually occluded by what was there before. And this is of course not really, as I said, there are a number of cases where depth buffering doesn't work, and the most notable one is transparent stuff, because if you're looking at a transparent object, you can also see what is behind it. So both objects actually affect the color of the pixels. So if we use depth buffering, we would either not see the object behind if it was drawn last. So that would look wrong, and you can sometimes see that as a bug if you don't disable depth buffering and use Painter's algorithm instead. So there are a number of cases where it doesn't work, but generally most geometry is drawn regular 3D graphics applications. They use depth buffering to achieve this depth sorting, and that's the other major operation that happens in this stage. There are these two, blending and depth buffering. Okay. Time to do a little quiz, as usual.